Let us continue with the convective mass transfer. This is the second mechanisms for this mass transfer. And the basic for mass transfer, which we have already seen, we have the concentration gradient that represent the driving force. And the direction of mass transfer is always from high to low concentration. We also have distance that represent the resistance. The distance can be given in meter, and the distance is also actually represent the path length of the mass transfer process. So this is basic mass transfer, and this basic mass transfer is applicable for both diffusion and also convective mass transfer. Now, we also have molar flux for diffusion last time, and the molar flux is governed by the Fick's law. The unit is mole per meter squared, and the relationship between molar flux and molar rate is given as follows. When molar flux times the area, we get the molar rate, which is equals to mole per second. The symbol for molar rate is NA bar. As of now, I will explain to you on the convective mass transfer. The equation that we are going to use is slightly different, and the molar flux is given as K, which is the mass transfer coefficient, multiplied with the driving force, which is the concentration gradient. For the convective mass transfer, these are the important things that we need to consider. The convective mass transfer is having faster rate than the diffusion. This is because of large eddies. So eddies in Malay is pusaran, and it can be represented by the symbol epsilon m. So what is eddies or pusaran? So this is the representative of eddies. So here you can see that when you have eddies, you have larger or faster rate of mass transfer via convection. In diffusion, we don't have eddies. So let us now consider the boundary layer. So we can have three different range: the laminar, the transition, and also turbulent flow. So here you see that the laminar occur only on diffusion, and it occur at the entrance region. In the middle region, there is a mix between diffusion and convection, but for turbulent, you have only convection. For convective mass transfer, we don't have any other choice, but we need to include the turbulent part. The turbulent part is the one contribute to the faster rate of mass transfer. Let us consider the general equation. So all of these general equations are familiar to you, right? Except that I have introduced the new term, which is the epsilon m, that represent the eddies. So this term I introduced for the first component of the equation. Okay, if you still remember, for the equation, we have the first term and the second term. For EMCD, by definition, the molar flux of component A is equals to the opposite direction of molar flux of component B with the same magnitude. Because of this, you can further simplify the general equation, but of course, you should maintain the eddies over here. When you derive this, you are going to get this expression. If your boundary condition is between 0.1 and 0.2, you have concentration of A at 0.1 minus 0.2 because you want to cancel out the negative sign. then your path length is the thickness, or Z2 minus Z1. Note that after you derive, you have the bar sign on top of epsilon m. Epsilon m is actually represent the average between 1 and 2. So where is 1 and 2? Let's say this is 0.1 here and this is 0.2. As we know, at this turbulent region, we are going to have well-mixed condition. So the concentration is actually in average the same at any particular point. So this is the definition of average eddies between 0.1 and 0.2 over here. When we derive, instead of normal eddies, we should take the average value. Next, there is also again another term that I would like to introduce. So if you see this equation, you want to replace this term with one constant. This is because we assume that the path length is constant, the average eddies is constant, as well as diffusivity is also constant. So this term is called Kc prime. So what is Kc prime? Kc prime, as I mentioned, is equals to that term, which is diffusivity of A in B plus average eddies and also divided by path length. So Kc prime here is actually represent the convective mass transfer coefficient for EMCD. So why EMCD? Because just now we saw the equation and the equation was related to NA equals to minus NB. So that's why this Kc prime is only applicable for EMCD. The unit is given as meter per second. So let's have a look when we have the gas phase mass transfer via convection. So Kc prime can only be paired with the difference in concentration. If you have difference in partial pressure, you use Kg prime instead of Kc prime. If you have the driving force in terms of mole fraction, then your constant is Ky prime. So you know that the value of this driving force in concentration or in partial pressure or in mole fractions are not going to be the same. So therefore, we can also say that Kc prime is not equals to Kg prime and not equals to Ky prime. But the product of Kc prime multiplied with the driving force of concentration is going to give you the same answer as the Kg prime multiplied with driving force in partial pressure. There is actually a relationship between all these constants, all these coefficients. So what are those? For instance, if you see here, you have Kc prime C equals to Ky prime. Kc prime C is actually also equals to Kc prime P over RT, because the value of C here from ideal gas law is equals to PRT. Okay, and then you also have relationship between concentration of A, partial pressure of A, and also mole fraction of A. So from this relationship, you can try to prove that the flux, if you calculate it using either combine the Kc prime with driving force in concentration or Kg prime in combination with partial pressure difference, or Ky prime combined with mole fraction, is going to give you the same molar flux. So you can pause this video, to see how you can convert this equation to this equation, for instance. Okay, let me show you how we can do that. So by taking this definition, we want to convert the second equation into the third equation over here. So we know this relationship, kg prime p is equals to ky prime. Okay, note that kg prime is not equals to ky prime, but when kg prime times p is equals to ky prime. So we take kg prime p over here to represent ky prime. Then for YA, we take this relationship. YA is equals to PA over P. So YA1 is equals to PA over P, PA1 over P. YA2 is equals to PA2 over P. So you have P outside and also inside the bracket that you can cancel out. So now you can see that the equation that you obtain here is similar to the second expression. Okay, so this indicates that this relationship or correlation can be used to interconvert between the value from mole fraction to the concentration or partial pressure. So how can you obtain this relationship? So actually, you can find it in table 7.2-1 in your textbook. What if we have EMCD for liquids instead of gases? So what are the equations that you are going to use? So you have three further equations in terms of concentration gradient. So here you see Kc prime C and also Kl prime. Since the driving force is the same, then you can say that Kc prime is equals to Kl prime. Next, you have the third equation. So since this is in liquid, the mole fraction is expressed in terms of X instead of Y. Okay, because for Y, you use that to represent gas. For liquid, you use X. And the coefficient is Kx prime. Okay, note that all these are for EMCD cases. Next, we can look into the table 7.2-1 from your textbook. Okay, so you have equations for EMCD and you also have equations for stagnant B. Pause this video and see how can you equate between the coefficient in EMCD and also stagnant B. I believe you have looked the difference. Okay, now the main thing that you can see from here is that for EMCD, the coefficient you have prime sign, but for the stagnant B, you don't have the prime sign. So the driving force is still the same, which is the concentration difference, Ca1 minus Ca2, but you have Kc instead of Kc prime for stagnant B. Okay, next is the conversion between mass transfer coefficients. The previous slides, I show you only the correlations for EMCD. So you can actually also find correlation between EMCD and also stagnant B. For instance, if you take Kc prime C, this is actually equivalent to Ky YBM. So for Ky is it actually equals to Kc prime C over YBM. This is how it looks like. You can also try for others. Of course, the first row here represent gases. The second row here represent liquids. Another things that you need to consider is the unit is not going to be the same for Kc and also Kx. Okay, so for Kc, Kl, Kc prime and Kl prime, you have the same unit. But when you compare with Kx, Ky, Kx prime and Ky prime is not going to be the same. You also have preferred unit, preferred SI unit for Kg and Kg prime. Okay, so what's next? So we want to look into statement B. So by definition, NB is equals to 0. So here, actually I want to show you how you can obtain the correlation between coefficient for stagnant B and EMCD. So if you look at this point, you can already see that for stagnant B, as I mentioned, you don't have Kc with prime. Okay, so you can actually correlate to the EMCD coefficient when you divide the EMCD coefficient with XBM. Okay, so that means the constant over here, okay, you have DAB plus average eddies over path length and also XBM. The things which is maintained is the driving force over here. Okay, so in summary, this is the correlation between Kc and Kc prime. Okay, so you should be able to calculate Kc if you are given with Kc prime, as long as you know how to calculate XBM. I hope you still remember. XBM can be defined as XB2 minus XB1 over ln XB2 over XB1. This is the first one for stagnant B and how we can correlate with EMCD coefficient. Next is, what if we express our molar flux in terms of mole fraction? Then this is the relationship between coefficient of mole fraction in EMCD as well as in stagnant B. Okay, because you know for stagnant B you don't have prime sign over here. Therefore, if we take this part together, we know that here is the correlation between the coefficient for X, that means for mole fraction for stagnant B, and how it can be correlated to coefficient of EMCD. Okay, so if the coefficient of EMCD divide by XBM, you are going to get coefficient of stagnant B. So to summarize, this is the correlation for gases for stagnant B. So you can express that in terms of partial pressure, mole fraction in gas phase as well as concentration. And for liquids, you don't express it in terms of partial pressure, but you express that in terms of mole fraction in liquid phase as well as in concentration difference. Actually also have the term YBM and also PBM. So where the YBM and PBM is correlated to, so you can of course refer table 7.2-1. So I hope that you can do this on your own. I finished the video explanation for this part. In the next video, you are going to see on how we can learn to estimate the convective mass transfer coefficient Kc. With that, thank you for your attention.